Okay, so we touched on climate economics a little bit in the other book by Roger Schmittner. Andy Dessler takes a slightly different approach, and I find it adds some value to what we already discussed. So he starts by looking at exponential growth, the concept of exponential growth, which you are probably very familiar with, and then he transitions that into various options for climate economics when it comes to how to reduce emissions through carbon taxes, how to account for costs of mitigation for future damages, which is what we are doing basically when we invest in climate mitigation, and also carbon tax, carbon cap and trade, and so on. So exponential growth concept is very simple. When the growth of something depends on the initial amount, it's basically exponential growth, and that's how interests are computed. For example, if you have a principal of P which you put in a bank with at an interest rate of R%, then the growth of that becomes P times 1 plus R over 100 to the N. So if you have $100 or 100 rupees at 10%, it should become from 100 to 110 in year 1. In the next year, so you earned $10 of interest, became 110. Then you are putting this into this kitty here, so you are now earning 10% on 110, so you get 11, so it becomes 121, and so on. And soon you see that in about 100 years, not about, it's reached $1.38 million. So 10% interest rate is an incredibly good investment if you can live for 100 years to enjoy it. But you can see how it grows. The doubling begins to add value, heavily loaded towards the end, right? So you are going here from a balance of $214 in year 8 to whatever it is after that. But you can see here, year 100 it's 1.38 million, and in year 101 it's 1.52 million. So begins to grow exponentially at the end, and this is how it looks. So this is a different chart, sorry. Consumption of water is a fraction in percent of total supply based on data in table 1, which is 10.1 here. So you can see how the use of a certain small fraction of the total supply in the beginning that keeps growing exponentially then can quickly overwhelm, because at some point it turns exponential, and in 100 years you are consuming more than 100% of the supply. So in the beginning you might think you are only consuming 0.1%, so it's not a big deal, and then you keep increasing it, and then before you know it you are out of control. But a better way to think maybe before that is to say you want to produce 25,000 rupees in 15 years, let's say, for college expense for your child. So you want to figure out with the interest rate of 5%, how much do you have to invest now to get 25,000 in 15 years. So there is a simple rule which goes with this kind of exponential growth. That's called the rule of 72. Basically, if you divide 72 by the percentage growth per year, then you are going to get the approximate doubling rate, the number of years it takes to double. So in 15 years you want to reach 25,000, and let's say you have 5%, then you can see how quickly you can double your money at 5% per year. So if you divide 72 by 5, you get about 14 point something. So if you want to double your initial investment in 15 years to 25,000 rupees at 5%, then you need about 14 point some years, which means you start with 12,000 now. In about 15 years you're going to have $25,000, rupees, dollars, whatever, at 5%. So the rule of 72 can be used to approximately estimate the doubling rate as well. So the example of water that I mentioned here, that I jumped ahead, is in this table here. So the amount of water consumed each year by a community, assuming that consumption increases by 7.2% per year. It's made simpler because you can divide 72 by 7.2. You get a doubling of in 10 years. So you start, let's say in year 2000, your consumption is 100 million gallons per year, and that's only 0.1% of the supply that you have available. You think that's not a big deal, right? 0.1%, that's pretty tiny. But if you increase at 7.2% per year the consumption, by 2010 you are going to be consuming 200 million. So you have doubled your consumption. You think it's still only 0.2%, so it's still pretty small. There is the chopper. But you keep going, and in 2020 you're at 400 million, still 0.4%, but then you can see that pretty soon you're going to hit 50 billion gallons per year at 50% of the supply, and if you're not careful you're going to consume 100% by 2100, because the doubling is at 10 years, so you're going to keep doubling and reach 100. So in another 10 years you're going to reach 200%, and then in another 10 years you're going to reach 400%. So obviously you keep doubling at 10 years, so the growth at the end is super exponential. This is the problem with doubling in exponential growth. But there is also a limit to exponential growth, because obviously you have now run out of water by consuming so much. It works for pretty much everything that grows exponentially, because there are resource limitations and there are all kinds of other things. So I switched the table here again, sorry about that, but it's just repeating what we said. The balance of $100 invested in year 2000 at an interest rate of 7.2% per year, which is very similar to the water problem we just talked about. So you are doubling at 10 years, so you go from 100 to 200 in 2010, 400, 800, and so on. And you can see that in 2090, after 9 doublings, you are at 51,200, and by 2100, in the next 10 years, you are going to be $102,400. You're going to be super rich because you doubled in the 10 years. So you can see the loading towards the end in these exponential growths, which looks like this. So a value of $100 invested at 14.4%, where the doubling is now 5 years, is going to be growing this way. So in about 140 years you are reaching the turning point, and then you're going to shoot through the roof very quickly to reach $1 trillion, heavily loaded towards the end again. Okay, so this is the crux of exponential growth, and the limitation is seen as a good case in this thing that happened in actuality. These so-called mortgages were being sold to people based on the assumption that the house prices will keep growing and growing. So even if you take a big mortgage and you cannot pay off, you can sell the house and recover the money, because the rates of the houses will keep increasing. And in fact, there was a rapid increase in the rates starting at some point. So there was a oscillation, or lower rates of increase and decrease in the beginning. After 2000 they did begin to grow, even though with a bit of up and down, and then people started borrowing more and more money, and banks started giving out crazy loans, and pretty soon people didn't care how expensive the house was because they could get the mortgage, and they thought they could always sell it for a higher price even though they bought it at a high price. And the housing prices, annual change in the house prices did jump. Obviously the defaults went up, the number of people who could buy houses at such exorbitant prices dropped, and then the housing prices collapsed, and then the rates of growth became negative, so everything went bust. There was a big financial crisis in 2008, and the bailout, that manipulation of the markets by infusing money changed things. So things have recovered, but you are probably not going to see that again till people forget such crazy things as ever-growing markets. So this is a good example of how exponential growth has limitations. Now, in the next podcast, we'll move to how we can use this same concept of exponential growth to think about investments for the future. Why? Because we are headed. What the hell happened here? That's where we are headed, in the sense of having to invest now to avoid future damages due to climate change, or to hedge against the risks of climate change impacts in the future. So you have to then value the cost of the climate damages in the future to see how much you have to invest now to bet against that cost. So you were looking for benefits of college funds in the future by investing now. This is the other way. You are looking at present value of a future cost. If a climate change damage is going to be 1 trillion in 2100, you want to estimate how much you can invest now to protect against that future damage. So this becomes quite a bit complicated in terms of using the same exponential growth rate, but now as a discount. So you want to estimate the present value of future cost. So it's slightly complicated, but we'll get there. And it's a very important concept because we are literally investing for future generations, not in the same generation. So the discounting of what the value of expense next year will be in the current dollar is very different than estimating the same thing for future generations, so beyond ourselves. So it's a little bit complicated, as we will see.